Okay, so this video is going to conclude the videos I have from this chapter on magnetism. And what are we doing? Well, we introduced the concept of Ampere's law. And Ampere's law has two sides, a left side and a right side. The right side says is asking how much current am I walking around? And that's the only question the right side is asking. So I am walking around a closed loop. How much current am I walking around? That's going to be something there. The left side, what is the left side asking? The left side is asking how does the direction of the magnetic field relate to the direction of the step? And in a bit more formal way, it looks something like this. So I have a certain strength of a magnetic field at a given step. I have a certain step size. I have a direction between these two guys. So I could call B and cosine theta, I'll call that B parallel. And so I could write this in a bit more succinct form, kind of like this. And in my opinion, you don't need to write it like this. I'm only introducing this step so that I match what the textbook has. So the component of B that is parallel to my step, that's B cos theta, times the step length around when I walk around a closed loop. Well, if I am walking clockwise and the magnetic field is clockwise as well, if the magnetic field is counterclockwise and I'm counterclockwise, that would have been fine too. This entire summation must be larger than 0. And what we're going to do is we're going to then ask, let's not just pick an arbitrary path. Let's pick a convenient path. One example of a convenient path is a circle around a wire with the wire right at the center of my circle. So notice that think of many little steps. So maybe my path is 10,000 or a million steps in total. For the most part, every step I take will always be parallel with the direction of the magnetic field. And so what we're going to do is we're going to make these steps very, very small. And if they're kind of small, we'll make them smaller still. And in the limit where these steps become infinitely small, basically we're alluding to calculus, where this summation will become an integral and this delta L will become a dl. But in the limit where the steps become infinitely small, then every step in this example, B will always be parallel with the magnetic field. So B times cosine 0 will just become B, because cosine of 0 is equal to 1. The magnetic field will have the same magnitude, the same amount at every step along the way, because every step along the way, you're always going to be the same distance from the wire. So you'll have the same strength of the magnetic field. You'll always be aligned with the magnetic field. So to call back the slide there, you'll always have the same strength of B. You'll always be aligned with the magnetic field. So this term here will always be the same. And the circular path I take around the wire is just a circle with radius r. So this delta L term will just be, the total length I take will be 2 pi r. So in the end, this B parallel delta L will just become B times 2 pi r, or the strength of the magnetic field at this distance from the wire times the total path length I take. And in this example, I get the left side of Ampere's law becomes B times 2 pi r. The right side of Ampere's law just becomes mu naught times I enclosed. I did not do anything like this. And now if I rearrange Ampere's law and solve for B, then I find at a distance r away from a wire, the strength of the magnetic field is mu naught I over 2 pi r. So we could use Ampere's law, which is right here, to prove the strength of a magnetic field a certain distance from a wire is given by this equation that we talked about from the slides before break. So what I'm going to do now is I'm just going to finish off the slides, then I will have example problems to give on this. So I mentioned the existence of a solenoid. What is a solenoid? Let's think about a capacitor. So when we first, way back in January, we were learning about electric fields. Point particles create electric fields. And I told you it is possible to create a uniform electric field in a region. And then we realized if you take two plates that are full of charge, you put the plates close together, have them be parallel with each other, you get a uniform electric field between the plates. So creating a uniform electric field is not really that big of a deal. Creating a uniform magnetic field is kind of similar, and that's done through a solenoid. So from the right-hand rule, the direction of the magnetic field from a loop of wire will point through the wire. So just have your thumb in the same direction as the current. And if the current is coming in and flowing this way around the wire, inside the wire, the magnetic field will point upward. And then magnetic fields have no beginning or end, so they kind of, so the magnetic field here will be pointing up. It'll go up and around, wrap around the wire. So the magnetic field created by one loop of wire is going to look something like this picture over here. Now, don't worry about this line here and here. This line, we say, does not affect the magnetic field in any significant way. Technically, I can't just have a current floating in space. I need somewhere for the current to come in and exit, so that's why we have here. But you could ignore these wires right here. What happens if we line up many loops of wire? So if I have many loops of wire that are all lined up with each other, I could then have a current magnetic field coming, but before this magnetic field line could exit this first loop of wire, this magnetic field line just instead is going to pass through the second loop of wire and through the third loop. And if you don't count these edges down here, then you get an approximately uniform magnetic field near the center of these loops. And what we're going to do next is, if we're relatively close to the center of these loops of wire, we have an approximately uniform or homogeneous magnetic field. So for a solenoid, inside the loops of wire, the magnetic field will be homogeneous or uniform. Homogeneous means the same everywhere. Outside the solenoid, in the ideal case, the magnetic field is going to be zero. It is possible to prove the magnetic field is zero outside the solenoid. It's a somewhat ugly integral to be completed. I'm not going to prove it. If you're really curious, just let me know and I could show you the derivation for it. Inside the solenoid, though, the magnetic field is going to be something else, and we're going to, in a future video, prove the strength of the magnetic field. Now, also notice right now, I said before that if you align your thumb with the wire and notice how your fingers wrap around the wire in the direction of the magnetic field. But when I was talking about the right-hand rule for the relationship between the direction of magnetic field and direction of current, I often said you have a curly part and a straight part. The curly part is your four fingers. The straight part is going to be your thumb. Now, let's look at this solenoid right here. I have a curly part, that is the wires that come, and the current comes out of the page up here. The current flows down and into the page down here, and then the wire will wrap around behind the page. If you wrap your four fingers, so your four fingers are coming out way up here, and your four fingers are going down, and your four fingers are going into the computer screen down here, you'll notice that your thumb points in the same direction as the magnetic field. So you could always have your thumb wrapped around the wire in the direction of the current and your four fingers wrap in the direction of the magnetic field. But another way you could do it is you could say if you have a curly part, that curly part will be your four fingers and the straight part will be your thumb. And the curly part could be the magnetic field, like a long straight wire, or the curly part could be the current, like the case of a solenoid. So a solenoid fundamentally is just a wire that is coiled and essentially wrapped around a cylinder. Now, cylinders are big, wires tend to be thin, so we're going to have many, many coils all wrapped up together. And we're going to get this current spiraling around a lot. And the magnetic field lines will, in a certain limit, be approximately uniform everywhere in the center of the solenoid. So a cross-sectional view of an ideal solenoid is going to look something like this, where we have current flowing into the computer screen up here. We have current flowing out of the computer screen down here. Have your 4 fingers point into the computer screen if they're above and out of the computer screen if they're below. And notice that your thumb is pointing in the direction of B. Your thumb is pointing to the left. And again, make sure you're using your right hand for this. So inside a solenoid, the strength of the magnetic field is given by this equation, where mu naught is the magnetic permeability of free space, the constant we use in magnetism a lot. I is the current flowing through the solenoid. L, this cursive L, is the length of the solenoid measured in meters, and N is the total number of loops. So I might have 10,000 loops of wire in a 10 centimeter long cylinder. So N could be 10,000, and the length of the solenoid would be, well, 10 centimeters, that becomes 0.1 meter. Now, it is probably more common that the N over L, cursive L, is written as lowercase n. So very often you will see the strength of the magnetic field inside a solenoid written something like this. And this is probably more common to be used. And outside a solenoid, the strength of the magnetic field is basically 0. So this is the ideal case for a solenoid. A real solenoid will tend to more resemble something like this, but to a really good approximation, and such as things we sometimes might use in lab, you would get a solenoid that looks something like this. So I'm going to stop the video here, and the next video is going to be some practice problems. And one of the problems is going to be we're going to prove this relation.